Hello everyone, Chaotician Drac here again. I was slightly delayed in getting my next video out. The interdimensional space has been a little weird lately, but broadcasting to you today once again from DIM 97773D. I believe you guys are in DIM 97743F. It's hard to tell for some reason, but anyway, welcome to the next episode. Today we're going to talk about chaos theory. Yay, that thing. So, but first I wanted to sort of describe what chaos is. It can be a little confusing given the subject, but the word chaos was originally a Greek word. My dad loves to remind everyone that chaos originally did not refer to the sort of panic, confusion, disorder, blah, everything that is the common meaning these days. It originally referred to the formlessness at the beginning of the Grecian cosmos, that which preceded all form in the universe for Greeks. So basically, in the beginning, there was this ball of stuff. All the earth and air and water in one thing. All the hot and cold as one. And it was dark and gloomy and stuff. Not long after, or whatever, who knows how long. Anyway, eventually entities came out. Or maybe that was the first thing that actually happened. And there was Tartarus and Erebus, and various others came and had sex and made more. But anyway, so there was all that. So chaos is sort of the antithesis of existence, or all existence at the same time. You get the idea that existence refers to, a part of things. It's not everything. If it were everything, it wouldn't exist. Existence is like a single thing going around doing and being. If it, everything at once is just sort of this static thing. So, anyway. So, formlessness has some connotations to it. If everything's this big blob of, non-form, it is sort of messy and not ordered, not structured, not regimented, and that's sort of what we think of with chaos these days. So, chaos theory, what is it? Where did it come from? There are a few origins to it. Over the past 100+ years, little bits and pieces came around now and then, but generally these things were never considered that important. They were sort of glossed over or forgotten. But around the early 1960s, both our dimensions, so something started happening. There were a few individuals who started noticing contrary elements of the natural universe that didn't abide by the standard, scientific understanding of how stuff was supposed to work. One of the most famous, if not the most famous example, Ian Malcolm came later, this dude named Edward Lorenz. So, don't know if you knew, but computers were originally sort of developed and worked on and built up for a very particular purpose. It wasn't games, it wasn't the internet, it wasn't even sort of general math stuff. It was specifically weather prediction. That was this thing they needed to be able to crunch tons and tons and tons of numbers in rapid sequence in order for certain sorts of calculations to be practical. People have been waiting for it for a while. The technology finally became available and people were plugging away at it. Weather prediction was not going especially well. People sort of thought that as soon as the computation was there, they'd be able to predict the weather and it'd be awesome. But so this project was going on. A fair number of people were involved. This dude, Edward Lorenz, was going over a chart thing that he had for a specific weather simulation. He let the computer print out stuff for a while, and then he wanted to come back to it. So he shut off the machine, and instead of restarting the whole thing, which would have taken longer, he started the simulation anew in about the middle, using data points that he'd already gotten. And so he put these things in, let the machine continue, and he went to grab a cup of coffee. When he got back, he discovered that there was the chart didn't match. It was, it sort of started out as the original one had, but then there started being little variations. And it's like there shouldn't be any variations at all. It's the same thing. And but after a while, even the two graphs showed no similarity whatsoever. He tried to account for this in a number of ways, but eventually all he could figure out was that what he figured out is that he had put in a rounded number for the input for the computer to run the simulation for, which was not the same as what the machine had been using at that point in the timeline on the data. And they were different. The thing is, they were slightly different, and math was making this assumption at the time, general assumption, probably no one even thought of it really, was that when you have approximate input, you will, approximately the same input, you will get approximately the same output in various algorithms and things. So this data sheet was like, what the hell? It's almost the same thing. It looked completely different. And so he invented or discovered or whatever this principle called special sensitivity to initial conditions. Basically, certain systems behave in such a way that even the tiniest variation in initial input, no matter how small, will eventually have drastically different outcomes using the same formulas and such. He determined after this that the future of weather prediction was doomed. The whole idea was a joke. Oh well. So this Edward Lorenz is credited for having come up with one of the first and still followed definitions of chaos when it comes to math. And that is when the present determines the future, but the approximate present does not approximately determine the future. So this was a new idea, and several people got wind of it. Not a whole lot, but several people started taking it seriously. And there were a number of mathematical problems at the time that needed to be solved that it was evident this chaos concept could be useful for. Weather, fluid dynamics, eventually they found out it could be applied to biorhythms and stock markets. Several common tools were developed for analyzing chaos, including phase space maps, bifurcation diagrams, and fractal mapping. And so you know what, I'm not going to bore you with that. It's all math stuff. I mean, it looks cool, but really it won't be useful for you. So there was a particular branch of these new chaos-focused mathematicians who were rather intrigued by the way that this new mathematics reflected nature and the real world around them. They were sort of finding that, well, I'll tell you what it comes down to. Measurement. When scientists and mathematicians or anyone go to measure something, they don't actually find the exact value. There's little decimals, like the temperature. This is a matter of precision. Is it 93.1 degrees? Is it 93.07 degrees? Is it 93.07258344? Who, you know, it's, you could go on forever in precision. And these variations in precision meant everything for the ultimate outcome of a chaotic system, if that's what you're working with. And so they were like, you know what? The real world is not so predictable. The real world is not so rigid and full of exact shapes and known tiny little things. We don't know exactly all these sorts of details. And so they were interested in what chaos could tell them about the real world. They looked at stuff like mountains, seashores, and leaves and their branchings and stuff, and they saw chaos. They were like, you know what, these are fractal patterns. These have mathematical formulas. Inexact though the outcomes may be, that's part of how they work. And everything was cool. Not everyone was so into this. A lot of people thought they were just nuts. Some people were actively mad at them, but they stuck with it. So some people were more practical than others, but there were various practical applications. So one of my favorite ones, this dude named Mandelbrot, famous for fractal diagramming and such. He was one day in a library or something somewhere looking up the distances, the official lengths of shorelines of various places on Earth. And he was surprised to find incredible differences between different sources on these measurements. He was like, why is this? These differences are way off. How can we account for this? So he looked into it, and he found out that the measurements had been taken by different means. And basically what he realized is that if you're this dude, some government worker, who goes to the seashore, puts down a little marker, the second marker, measures the distance, even if it's only like a few yards or something, and then goes to the next one, he's measuring these little distances at a certain scale. Don't care how precise he was at what he was doing. He was measuring at some observable scale, standing there. So that's one. Then you get a measurement from outer space and satellites, and they're not going to see the same thing. And they're, even if they do like, pixel level measurements, it's not going to be the same distances as the dude that was on the ground. And in some imaginary version of this, if you took a microscopic researcher, put him on the ground, and had him measure these little distances for days until he got all the way across some piece of shore, it would be different still. Generally speaking, the smaller scale you go to measure, the more distance you're going to get. Because when you have, it's the difference between like this line and then this complicated line, whatever it looks like, greater detail is going to add distance. Doesn't matter what it is. So he came to the conclusion that any seashore is potentially infinitely long. No, not just really long or something, but infinitely long. Because you could go potentially to smaller and smaller and smaller and smaller scales and always get a longer measurement. It's kind of freaky. The seashore is infinite. It's fun. That's fractals for you. Infinite regression, scale stuff. Anyway. So, the butterfly effect. Very popular chaos thing. It's more well known than the term chaos theory. I'm pretty sure. There might be some difference between our dimensions, but anyway. Yes, I've seen the movie from Your World. Ian Malcolm brings it up. That's nice. So, as they say, this butterfly in Peking or whatever, flaps his wings, and in Central Park, you get rain instead of sunshine. Isn't that nice? It's a reference to the way weather models show that, you know, the smallest deviations in the starting conditions can have drastically different outcomes and results. So this butterfly has tiniest little variation, and there's this massive storm. It's like, okay, I don't know how many people actually believe that one. I really, but as far as I can tell, I've thought about this, and as far as I can tell, the most you could really see that has any truth to this at all from this example is that you could measure, if you were able to measure two different timelines, you could find one where this butterfly does and doesn't flap its wings, and there's rain in one and sunshine in the other. Is that causal? No, I really don't think so. So the thing is, the way that this butterfly effect example would work is if this one position where the butterfly was somehow the determiner for the state of the weather in New York. And it's like, what? There are like billions of butterflies around, other insects, people, trees, all this stuff, doing motions or waving their hands or whatever, and all these things affect the weather, the air direction. And then there's something like the jet stream, which is huge, and it's sort of a lot stronger than all those things. Of course, the details can pile up into their own sort of globular things, but this one butterfly wasn't in charge of what was going to happen to that. It was a sort of collective thing. And then, anyway, there's this famous story, A Sound of Thunder. And it's got this group. There's this commercial company who sends people back in time to hunt dinosaurs. It's kind of funny. And you know, they kill dinosaurs all the time. They've been doing it for a long time. But on this one trip in the short story, this dude messes up or something, and the guy in charge is like, I want you to go collect the bullets from that T-Rex. We can't leave anything here. It'll affect the timeline. So he goes and does this, and they get back to the real time, and there are all these subtle differences, and they're like, what? Words are spelled slightly differently, the atmosphere's off, and it's strange. And the dude looks, and there's this butterfly on his shoe. And then he goes on to say that, so this butterfly, because it died and it was on his shoe, some predator wasn't able to eat it, and then he starved. He wasn't able to feed his family. They starved. They died. The population of this creature was altered. Migration patterns changed because of the predators and all this. And then in the future, these different herds going in different places caused the humans to migrate differently, and you know, we end up with these little changes everywhere. It's hilarious. Just the way causal density works is that's not it. So you know, there are these causal network thingies. They're full of determiners, and each, you know, it contributes in what it does, and there are all these little variables, and they go into the network, and stuff comes out. But you know, you want to know something like that, you'd have to measure each one exactly, each of these little variables exactly, which you can't, and you need to know every determiner in the system, which you don't. So it's bullshit. It's stupid. You know, Andre Halverson, so I'm still trying to figure out what that chaos seed thing is that he was trying to find. Is, you know, maybe it was some sort of the initial conditions for the entire universe. And it's like, can you imagine what an insane objective that is? It's impossible enough to find the exact initial conditions for any real object, let alone everything. So, you know, maybe he had like this thing, sort of a constant adaptive precision increase built into the machine or something, so that it was constantly refining the precision of the data as like part of the mechanism built into it. Maybe that would, I don't know. Or maybe the answer was 0. You know, who knows? Excuse me, I have to take this. Yeah. That's a friend of mine. Anyway. So, that's pretty much all I wanted to say. Chaos is, you know, it's a variation. I think there's a possibility that trying to assign numbers to chaos is actually one of the funniest things there is. It's almost like chaos theory is showing how stupid math can be, how idiotic we can be for thinking that these numbers and formulas and rigid structured things actually describe what's going on. It's almost sad because it's, you know, it's still got these numbers things in it. And these people, you know, the people who are still in the regular science and math are like, you guys are stupid and idiots. And it's like, yeah, that's what they would think. And the chaos theory people is like, you know, they're still with the numbers. They get the natural world thing, but they haven't quite finished. Anyway, that's chaos.